Now this part is tricky. What happens if you rotate axes? Lots of formulas, lots of trigonometry here. The steps are all shown. This diagram is actually particularly good to show how we transform coordinates. That u is x cosine theta plus y sine theta. V is y cosine theta minus x sine theta. And we can see that. So here's the x coordinate. Here's theta. So x cosine theta gets us, here's the element. Here's the right triangle that we do. So x cosine theta gets us to here, right there. The x coordinate times the cosine theta is this line segment. And the y coordinate times the sine of theta gives us this line segment right here. So we add the two together. Similarly for the y-axis, the y cosine theta, so here's theta, and the y coordinate times cosine theta would give us this line segment here, which we translate over to here. Here's the y, here's y cosine theta, the length of y cosine theta. And now we have to subtract the x sine theta. Here's x sine theta right here, this line segment right there. So now we have to subtract the x sine theta. Now you can see how from this diagram we can get those transformation formulas, and those will be important. So let me erase all the ink on this, and let's go on. I'm not going to erase all the ink, some of it anyway. So u is going to be the integral of y squared dA. So the rotation about the u-axis is going to be the, I shouldn't say y, yeah, y cosine theta minus x sine theta squared, v squared dA. And we crunch numbers. Expand the binomial, identify ix, iy. So this next step is pretty easy. This step isn't so easy. Cosine squared is cosine 2 theta plus 1 over 2. That's the formula for cosine squared. Sine squared is 1 minus cosine 2 theta over 2. And then this is 2 sine theta cosine theta is sine of 2 theta. So we use some trig identities. Now we can rearrange. We get ix plus iy times 1 divided by 2. And then we get the common factor cosine 2 theta. So we get ix minus iy times the cosine of 2 theta minus ixy sine 2 theta. So this is our finished formula for this, for I sub u. I sub v is very similar. You'll notice the I sub u is ix plus iy over 2 plus an expression. I sub v is ix plus iy over 2 minus the same expression. So this will be important later. The product moment of inertia in the UV system is, we're going to take the well, here's the, here we go. Here's IUV. So it's very similar. We're going to have we're going to take the binomials, multiply them together. We're going to identify this. After we multiply binomials, this is cosine 2 theta right here. This is sine 2 theta over 2 right here. So we get this expression for IUV. And then J doesn't change. If we notice, remember I said that IU is this, the IX plus IY over 2 minus, plus an expression. IV is this minus the same expression, so we're just adding these two together to get the J's, which works out to be IX plus IY. So J doesn't change between the two coordinate systems. Now the question to ask, what is this good for? What angle can you place the coordinate system, the principal axes, so that the moment of inertia is maximized or minimized? And we just take the derivative of IU and IV. DIU d theta equals negative DIV d theta. Set them equal to 0 at the principal axes, and you get this trigonometric expression when you do your calculus. Notice that it equals negative 2 IUV. And so just finding an expression, tangent theta p is this. At this principal axis angle, or if u or v are an axis of symmetry, UV equals 0 at the principal angle or axis of symmetry. That means an axis of symmetry is at theta at this principal axis angle. One of the two is maximized and one of the two is minimized. IU is max and IV is min, or vice versa. IU is minimum and IV is maximum. There are two possible solutions 90 degrees apart. So these expressions will be needed when we get to figuring out what is the maximum, what is the minimum. So the cosine of 2p is given by this, and the sine of 2 theta p is given by this. And then we go to the next slide. We use those expressions to find I min or I max. We just substitute the sine and cosine angle expressions into the formulas for IU and IV, and we find the I min max expression given like this. Moore's circle. Now, complicated math. So I min and I max. So here's what theta p represent. Negative IXY, positive IXY. The maximum here, and here's that length. And this is about, here's O. Here's a different circle, by the way, O. So you're at plus or minus this distance from the center of the circle, and the radius is this. This just repeats the previous drawing, by the way. Now, the way to visualize this is to plot the points IX, IXY on Cartesian paper, and the point IX, negative IXY, and draw a straight line. The center of that straight line becomes a circle, and draw the radius of the circle. There's the radius of the circle right there. There's the radius of the circle. This then becomes I minimum, which is at Ix plus Iy over 2 minus the radius. Maximum at Ix plus Iy over 2, that's where the center of the circle is, plus the radius. And then tangent theta p Ixy over Ix minus Iy over 2. The circle helps you visualize all those prior complicated formulas. That's why we do it. Next slide.